This next type of reaction that we're going to look at is when you add an acid to a base. These guys are called neutralization reactions because the H plus from the acid usually comes together with the OH minus from your base to form water. So just some examples here. So for A, it says if you mix some potassium hydroxide, so potassium hydroxide's KOH, and then you mix that with some hydrochloric acid, HCl, and then it says, well, that's H plus OH minus makes water. So where are the K plus and Cl minus ions? Where'd they go, right? Well, potassium hydroxide is a strong base, so we would break that up into K plus, OH minus. Hydrochloric acid, strong acid, H plus, Cl minus. So when we react all these ions together, the K would try to go with the chloride, and H would go with hydroxide. So K plus, Cl minus, well, potassium chloride, if you know your solubility rules, is aqueous, so we would show that guy broken up. The H and the OH come together to make water, a liquid. We keep solids, liquids, and gases together. We only ionize things that dissolve in water, soluble, or they're strong acids and bases. That potassium and that chloride, those guys are spectator ions. They're exactly the same on both sides. And so what we have left here in the net ionic equation is what's left over after you cross out those spectators. So whenever you have a strong acid plus strong base reaction, that's what's going to end up happening, is you'll get this guy here as your net ionic equation. So here's another example of this guy. Solutions of nitric acid, sodium hydroxide, and it asks you, are these acids strong or weak? Well, nitric acid is on our strong acid list, H plus, NO3 minus. Sodium hydroxide's on our strong base list, Na plus, OH minus. When these guys start to react with one another, the H plus will go with the OH minus. It's going to make some water in our neutralization reaction. And the Na would go with the NO3. Well, sodium nitrate, all alkali metals are soluble. All nitrates are soluble. So that sodium nitrate product we would write as ions. It does not form a precipitate. So we would keep them broken up. Our water would come together. So once again, spectators cancel, just like in the previous example, because it's another strong acid, strong base. You're going to get the same answer that we did up above. Happens every time. What if it's not a strong acid plus strong base? So it gives you an example here of adding sodium hydroxide to acetic acid. Acetic acid is not a strong acid, so we do not break this guy up into hydrogen ions and acetate ions. Instead, we keep it together as a molecule. Well, that sodium hydroxide is really Na plus OH minus, right? You have the Na plus and this OH minus. Well, the H from your acetic acid goes with the OH to make this water. And then this sodium ion goes with this acetate ion to make sodium acetate. Well, sodium acetate, anything with those sodium ions in it, soluble, broken up. And so the sodium ions become spectators and they cancel out, leaving just what you see here. right? That's all that's left. When you have an acid-base reaction, this is a huge, huge, huge idea in acid-base chemistry, as you'll see throughout the year, that when you have acid-base reactions, that hydrogen ion is transferred from the acid to the base to make water. So many, many, many acid-base reactions involve that H plus ion is moving over to something else, right? So this hydrogen H plus ion kind of moves over here, right? And makes water and leaves that acetate ion behind. Here's another example of that hydrofluoric acid. Hydrofluoric acid is not on our strong acid list, so we keep it together. If we're reacting that with potassium hydroxide is a strong base, so we show it broken up. Well, that H is going to combine with this OH to make our water, and this K is going to combine with this F to make potassium fluoride. Well, potassium fluoride, anything with an alkali ion in it, is very, very soluble in water, so we show that as being ions. That potassium ion is going to be a spectator. It's going to cancel out and go away. So all you'd have left is hydrofluoric acid, hydroxide ion, goes to water, looking crazy there, water, and fluoride. Once again, we have this transfer of a hydrogen ion over here to make water. The fluoride ion gets left behind. Here are a few more examples of that hydrogen ion transfer there. So if you have ammonia is NH3, nitric acid is H plus, NO3 minus. That nitrate is going to end up being another spectator ion. It's going to cancel out and go away. But once again, you can see this H plus is moving over, right? And forming that ammonium ion in all of these examples, right? Here's an H moving over to form that NH4 plus. Here's an H moving over to form more NH4 plus, right? So be on the lookout for that proton transfer that's taking place between ammonia, NH3, neutral, and the ammonium, NH4 plus, ion. This guy, you might be wondering, wait, what's going on here? Well, you still have that transfer. The H plus from our hydrochloric acid is going to go with the bicarbonate part of our sodium bicarbonate. When we move over there, H plus with HCO3 minus, you get H2CO3. But you might recall, I said before, H2CO3 is not a very stable acid, and it's always going to break down into water and carbon dioxide. So, just a few more examples of that hydrogen transfer taking place. And the other ions that you don't see listed, like this talks about sulfuric acid. Where's the sulfate, right? Potassium fluoride. Where's the potassium? Those ions must be spectators.